Have you ever just looked at a solar panel, that simple, dark rectangle, and really wondered how it pulls off this everyday magic? How it turns pure, raw sunlight into the power that lights up our entire world? Well, get ready, because today we're going on that incredible journey. We're going to follow a single particle of light from millions of miles away, all the way to the socket in your wall. And just to set the stage, to really get the scale of what we're talking about, think about this for a second. The amount of raw energy the sun pours onto our planet in a single hour is enough to power all of humanity for an entire year. It's this constant, unbelievable cosmic downpour of pure energy. So that right there is the big question, isn't it? How does this silent, motionless panel on a roof manage to catch and tame that immense storm of energy? Okay, let's dive in. The answer starts smaller, way smaller than you can possibly imagine. To solve this puzzle, we have to shrink ourselves down. We've got to stop seeing solid objects and start seeing an ocean of tiny particles. And our whole story, it all begins with just one single drop in that ocean, a particle of light called a photon. You see, the entire miracle of solar power really hinges on this one beautiful principle, the photovoltaic effect. And it's simpler than it sounds. Photo means light, and voltaic means electricity. So it's literally the process of light creating the potential for electricity. But, how does a particle of light actually do that? So forget any ideas about particles crashing into each other like tiny billiard balls. It's way more elegant than that. A better way to think about it is that a photon acts like a tiny key made of pure energy. It arrives at a silicon atom, it finds an electron that's locked in place, and it doesn't just knock it away, it precisely unlocks the bonds holding it there. In that instant, the electron gets this jolt of energy. It's excited, and now it's totally free to move around inside the material. So great, we've unlocked millions of electrons. We're done, right? Well, not quite. A bunch of energized electrons just bouncing around in random directions, that isn't a current. That's just heat and chaos. It's like a mosh pit. To get useful power, you need direction. You need flow. And this is where the real genius of solar panel design kicks in. Engineers create this brilliant structure I like to call a one-way electronic slope. They take two super thin layers of silicon and they treat them differently. The top layer, the N-type, is given a surplus of electrons. That's the top of our hill. The bottom layer, the P-type, is designed to have these empty spots, or holes, where electrons would absolutely love to settle. That's our valley at the bottom. Now, when you put these two layers together, something amazing happens. An invisible electric field forms right at the boundary between them. And this field, it acts like a perfectly smooth, incredibly powerful one-way slide. So the moment an electron is freed by a photon, this field grabs it and forces it to go in only one direction, straight down the slope. And just like that, chaos becomes order. Okay, so we've seen the science from 30,000 feet, but to really feel it, to really understand it, let's zoom all the way in. Let's experience this whole journey from the inside. For the next few moments, I want you to imagine you are an electron. Before the sun comes up, this is my world. I am completely still, held tight in the perfect repeating lattice of a silicon crystal. I'm bound. I have no energy of my own. There's nowhere to go. And then, bam, it happens. A particle of pure energy, a photon, finds me. It's not a collision, it's a transfer. The key turns in the lock. The bonds that held me for so long just shatter, and I am suddenly vibrating with this incredible new energy. I am free. But before I can even think about moving, I feel it. This undeniable, invisible pull. It's that electric field, that one-way slide we talked about. It gives me direction. It gives me a purpose. And there is no fighting it. There's only one way to go, and that's down. And I'm not alone anymore. I am immediately swept up with millions, no, billions of other freed electrons. All of us push down the same slope, all in the same direction. The chaos is totally gone. We're not a random mob anymore. We're a rushing river, an organized, powerful flow. We are a current. Our journey takes us along these tiny metal highways on the panel surface, into a wire, and finally, to our destination. We rush into something like a light bulb, and in one final, collective burst, we release all of that energy we captured from the sun. Our journey ends, and in its place, there's brilliant, useful light. Okay, let's zoom back out from that incredible little story. That entire journey we just saw is only possible because of one of the most common elements on Earth. But, and this is a big but, turning it into a solar cell is anything but simple. Now, you've probably heard that solar panels are made from plain old beach sand. The reality is way more complicated. It starts as super high-purity quartz sand, which is then melted and purified in this incredibly intense, energy-hungry process. The whole goal is to grow a single, massive crystal of silicon that is more than 99.999% pure and almost perfectly structured. Why go to all that trouble? Well, because any flaw, any little impurity, is like a pothole on that electronic slope. It can trap our electrons and waste their energy. In the world of solar, purity is efficiency. All right, so here's a question you've probably asked yourself just by looking at them. If these things are all about light, why are they always dark blue or black? Wouldn't a brighter color make more sense? Well, it really just comes down to some very basic physics. Think about it. A white shirt on a sunny day feels cooler because it reflects most of the light that hits it. For a solar panel, that reflection is just wasted energy. It's all those photon keys just bouncing away without ever unlocking an electron. A dark surface does the exact opposite. It absorbs as much light as possible, soaking up all those photons so they can get to work. You know, for decades, silicon has been the absolute workhorse of the solar industry. It's reliable, it's proven, but the quest to capture sunlight even more efficiently is leading scientists to explore some absolutely incredible new materials. And believe me, the future is looking very, very bright. To get a handle on what's next, let's use another quick analogy. Think of the crystal structure of the silicon we use today as a flat, two-dimensional net. It's just trying to catch those photons as they fly through. Now, imagine a new material, one whose crystal structure isn't a flat net, but is instead shaped more like a three-dimensional funnel. Well, that's the big promise of a new class of materials called perovskites. So, what's so great about perovskite? Well, its unique crystal structure is just incredible at its job. It basically funnels the light's energy right toward freeing an electron, which means it can be way more efficient. And here's the kicker. It can be made into a kind of ink and literally printed onto flexible surfaces. Imagine solar-powered windows or backpacks or even jackets. Now, silicon is still the stable, proven champion for now, but perovskites are opening up a whole new frontier. It's a total game changer. And that brings us full circle. We started with the journey of one single electron, unlocked by one single photon, and given direction by one invisible field. But when you multiply that tiny, elegant process by trillions, happening every single second across miles of solar farms, you get something incredible. You get the lifeblood of our modern civilization drawn straight from the sun. It's just such a powerful reminder, isn't it, that sometimes the biggest revolutions, the most world-changing technologies, they all begin by just understanding and telling the smallest of stories. It kind of makes you wonder, what else is out there just waiting for us to discover it, if only we listen closely enough?